and today we deal with second theorem of our section about implicit function. So let me call it implicit functions determined by a system of equations. So theorem 1 was about one function, implicit function, determined by one equation. Now we are talking about a system of equations and several functions. So suppose fj of x1 so on xn y1 so on ym are differentiable in a neighborhood of, okay, let me call it U of the point x not y not. Let me write it in coordinates. Not. And also more conditions should be satisfied. Yeah, I should also mention this is valid for every index j, but I'll put the conditions for the index j after everything. So partial derivatives of fj with respect to yk are continuous in U. Now let me indicate indices j from 1 up to m and k from 1 up to also up to m. Next condition is at the point fj proto x naught y naught. There are zeros for j from 1 up to m, and the Jacobian f1 so on fm, and with respect to variables y1 through yn at x naught y naught is not 0. Then for arbitrary epsilon 1 so on epsilon m positive, there exists delta positive such that for all x in the cube, same cube as in theorem 1, so I'll not specify it now, so it's the same notation as in theorem 1. There are functions yj equals to phi j of x1, so on. Okay, let me use vector notation here. There are functions uniquely determined in by the following. Systems of equations f j of x y equal to 0, j from 1 to m, and y j equals to phi j of x, j from 1 up to m are equivalent for xy in the Cartesian product of our cube times product of the intervals y j naught minus epsilon j times y j naught plus epsilon j. Yeah. Moreover, functions phi j's of x, j from 1 up to m are differentiable at k delta x naught. Of course, it is possible to write down also the formulas for partial derivatives, but I plan to do it later, not in the formulation of the theorem. You see, this is rather huge without formulas for derivatives, right? So, okay, now proof. Proof by induction in M. So the first step of induction, step 1, M equals to 1, that is theorem 1. Why? Because look, So if m equals to 1, we have just one variable y1. Then what is Jacobian? Jacobian here is, so if we have just one function here and one variable, then the determinant of the order 1 by 1 is a number. So the Jacobian here is just this partial derivative, and the condition that it is not 0 at the point x0, y0 is precisely the condition from theorem 1. Moreover, we have just epsilon 1 positive, so everything is satisfied. I mean, all suppositions of theorem 1 are satisfied. Hence, indeed, we can find unique function phi 1, y1 equals to phi 1. That is precisely what was asserted by theorem 1. So the first step of induction, m equals to 1, is precisely theorem 1. Okay, so we proceed with the main step. The main step, right? So we suppose the theorem 2 is valid for m minus 1. Now, without loss of generality, we'll put extra supposition. So let me consider the Jacobian. So the Jacobian, I'll omit the point. So if I'll forget about the point, then it will be a little bit shorter. And let me write explicitly, and I'll consider also one more entry of this determinant. So here we have partial derivatives of the function with number m minus 1. And lastly, partial derivatives of the function with number y1. So what we do without loss of generality? We know this determinant is not 0. And if it is not 0, then at least one of minus of the order m minus 1 is not 0. So without loss of generality, I'll suppose that the principal minor is not 0. Why we can do it? Because if some other minor is not 0, then we can rearrange functions, just make a transposition of functions, or rearrange variables, yks, to be sure that just the principal minor is not 0. So without loss of generality, what is without loss of generality? I'll suppose that the principal minor which is that one, at our point x naught, y naught is not 0. So that is our supposition without loss of generality. Okay. Then consider now the system fj of x1, so on, xn, y1, so on, ym minus 1, ym equals to 0, j from 1 up to m minus 1. So we consider the first m minus 1 equations. Forget about the last for a while. Then you see our supposition that this Jacobian is not 0 means that all suppositions of our theorem are satisfied when we replace vector x, let's say x tilde x now, is x1, so on, xn, and also ym. And our y tilde vector is y1, so on, ym minus 1. So, roughly speaking, look, we have precisely m minus 1 equations, and we want to solve them with respect to those variables, from y1 up to ym minus 1. So all other variables are considered as parameters. So then, by induction hypothesis, what we can do by induction hypothesis? All suppositions of theorem 2, better to say, of the induction hypothesis of theorem 2, are fulfilled. Hence, for arbitrary epsilon 1, so on, epsilon m minus 1 positive, we can find delta 1 positive such that for all x tilde in the delta in the cube k delta 1 x naught tilde. So what is x naught tilde? X naught tilde vector is the following: x1 naught, so on, did I put no, x n naught and y m naught, that is x tilde 0. So for arbitrary x tilde in such cube, there are functions. Okay, how to denote them? Let me denote them by capital phi. So there are functions y, j are equal to capital phi j of x1, so on, xn, ym, j from 1 up to m minus 1. So there are m minus 1 functions such that for all x and for all y, so in such a product, x tilde bar times product from j from 1 up to m minus 1 y j 0 minus epsilon j y j 0 plus epsilon j in such a Cartesian product, if x tilde y tilde is in this Cartesian product, then that system of equations is equivalent to the system of equations if we substitute. Okay, I'll rewrite that system. Equals to 0, j from 1 up to m minus 1. So, you see, we can solve that system using those functions. Okay, now what we want? We want to solve somehow also the system with respect to the remaining variable, ym. So ym was considered as a parameter. So ym was among axis with tilde. Okay. So how to do it? Substitute yj equals to phi j, j from 1 up to m minus 1 into capital F, m. So what we'll obtain? We'll obtain such a new function. So fm x1 so on xn. Now, you see, I have the remaining function. I substitute first variables are the same. Then variables from y1 up to ym minus 1 should be replaced by those functions. So x1 so on xn ym so on phi m minus 1 x1 so on xn ym, and lastly ym. So that is a new function which I'll denote by psi of maybe psi m of x1 so on xn ym. Right? So now what we want to do? First of all, let us substitute into the function psi m values with index 0. So what happens if we'll substitute values with index 0? Then what happens with capital phi? So if we'll substitute indices with 0, then as we know by construction, we'll obtain precisely yj naught here. So yj naught equals to capital phi j of x1 naught so on x and naught ym naught by construction, because for j from 1 up to m minus 1. Because what we did, we solved that system of equations, and if here we'll put indices with x1 from to xn and also with ym, put zeros here, then also zeros. If we put them here, then we have equality. And as we know, that point is in this set, so systems are equivalent, so yj naught should be also defined by this equation. Okay, should satisfy, so sorry, not defined, should satisfy those equations. So, look. So it means if I'll substitute here indices with zeros, then these are precisely yj zeros, and then by supposition, this supposition, for j equals to m, the function fm, when we substitute all variables with index 0, is equal to 0. So this capital M should be 0, so our function is 0. Okay, now I want to apply theorem 1 to the function psi m. So we'll need to check that all suppositions of theorem 1 are satisfied for the function psi m. And of course, we have to start with differentiability. So differentiability follows from chain rule for functions of several variables, because by induction supposition, right, by induction hypothesis, all functions capital phi are differentiable. So all functions phi are differentiable in this cube. So when we substitute them into this list of variables, then the resulting variable will be here, once again by induction hypothesis. And of course, I should suppose that this is in our neighborhood U, where everything is satisfied. I mean, all suppositions of our theorem are satisfied, so delta and epsilons are sufficiently small. Okay? Yeah, so to satisfy that supposition, of course, I cannot take here arbitrary large epsilons, so they should be arbitrary small. So maybe I should include here arbitrary small. So, and if this set is in our neighborhood, then automatically the function capital Fm is differentiable, so psi m is differentiable. Now we have also another supposition. We'll need to check that this partial derivative at the same point should be not 0. So that is the supposition which we have to check that it is satisfied. Otherwise, we cannot apply theorem 1. So theorem 1 works when this partial derivative does not equal to 0. So now I plan to go to the proof of this inequality. Okay. Let's start to compute this partial derivative. Let me do it here. So the partial derivative of psi m with respect to ym, I'll omit the point. By the chain rule, we can compute it. So, look. By the chain rule, we have a function of several variables. If we want to find a derivative with respect to a variable. Then we need to differentiate firstly the outer function with each of places where our variable appears, and it gives us the sum k from 1 up to m minus 1. So firstly we need to differentiate the outer function, that is fm with respect to variable yk. This is the place y1, the place ym minus 1. So we differentiate with respect to places. And then we need to multiply the derivative of this function, which is on that place, with respect to variable ym. So phi k over dy ym. But also we have one more place where ym appears, its own place. So plus df m over dy m. That is our partial derivative. So let me numerate this equation by 1. Okay. Now I want to go back to this system of equations which we solved, right? So what means that we solved this system of equations? It means that when we substitute all those functions into our functions capital Fj, then we'll obtain identities here in this cube. Identities are completely similar to this, right? So let me write those identities. Those identities will be as follows: x1 so on xn, then capital phi 1 of x1 so on xn ym, so on capital phi m minus 1 of x1 so on up to xn ym, and ym equals to 0, j from 1 up to m minus 1. So those identities are satisfied everywhere in our cube k delta 1 x naught, delta 1 x naught tilde. And when we have identities, all functions here are differentiable. Hence, once again, we can apply chain rule for the functions of several variables. So if we'll differentiate those equalities with respect to ym, then we'll obtain similar equations. Let me write them here. So I'll start with j equals to 1. So we differentiate equation with j equals to 1. What we'll obtain? Partial derivative of f1 with respect to yk, ym plus partial derivative of f1 with respect to ym, and so on. The last for j equals to m minus 1, 0 equals to, because we differentiate identical 0, right? That is identical 0. Sum k from 1 up to m minus 1, partial derivative of f m minus 1 with respect to yk times partial derivative of phi k with respect to ym plus partial derivative of f m minus 1 with respect to ym. So those are the equations. Let me call them by 2. So equation 1 was obtained by differentiating the definition of our function psi m, and system of equations 2 was obtained by differentiating other functions f, j when we substitute our capital phi's. Okay, now I need to heavily use, in fact, some facts from linear algebra. So go back to our determinant here. Our determinant, our Jacobian, right? Here it is written, our Jacobian. And let me recall that we can compute the determinant, arbitrary determinant, by expansion in elements of one line or column, right? That is called Laplace theorem, right? So we can expand our determinant in elements of the last column. What it gives to us? It gives to us the following equality. And so our determinant can be written, okay, I'll write explicitly dym times delta 1 plus so on plus df m minus 1 with respect to ym times delta m minus 1 plus df m with respect to dym times, in fact, yeah, firstly I write with delta m. What are delta k's? Delta k's are algebraic complements, right? So how to obtain coefficients in the expansion? What we need to do? We multiply this by what? We erase the line and column, right? And consider the determinant, which is remained, right? And multiply by minus 1 in power sum of numbers of line and column. That is called algebraic complement. I don't need to recall in details what they are, those algebraic complements. Let me denote them by delta 1 and so on, right? So that is the property of determinant, right? Now, what is delta m? What is delta m? Delta m is algebraic complement of this last element of this column, right? So minus 1 to the power m plus m is 1, right? So this algebraic complement is precisely our principal binom, which is not 0 at x not at y not, right? So delta m, let me write here, delta m is our principal determinant. principal minus. Okay, let's have a break at the moment. Let's continue. So, now numbers from delta 1 up to delta m are defined, and let us multiply the equation 1 by delta m and equations in the system 2 multiplied by delta 1, so on, delta m minus 1. So we multiply those equations by those numbers and sum up all of them. Sum up all of them. So let me write down the result. In the left-hand side, what we have? We have just delta m times this partial derivative. Delta m times partial derivative of psi m with respect to ym equals 2. Now, let us, if we'll sum up those terms, then let me write down it as follows. So, let me enumerate equations by indices j, j1, so on, jm minus 1, and here j equals to m, right? So, firstly, it doesn't matter. How it is easier to understand. So, look, what I want to do. I want to sum up those sums, right? That will be double sum, and I'm thinking in which order it is better to write it down. Yeah, I think I should change the order of summation. So, outer sum will be in k. So, sum k from 1 up to m, minus 1, sorry, m minus 1. So, partial derivative of phi k with respect to ym is a common multiplier. You see, it is the same for every equation. And in brackets, we'll obtain what will be given by multiplying by deltas of those terms and summing them up. So that is, I'll start with j equals to 1, or maybe j from 1 up to m, with sum up all of them. Delta j times partial derivative of f j with respect to y k. Yeah? That is the result of summing up of all those terms, plus remaining term, the remaining term, sum j from 1 up to m, delta j times dfj over dym. Now, I raised here the determinant. It was not a good idea, but let me draw it once again. Our determinant Jacobian it was the following. This was our Jacobian. This was our Jacobian. So what is written here? For example, when j equals to 1, oh sorry, when k equals to 1. So look, what happens if k equals to 1? If k equals to 1, then we have partial derivative of fj with respect to yk. These are elements of the first column, right? And we multiply them, you see, multiply them by delta j's. And delta j's are algebraic complements of the related elements of the last column, right? So multiply the first element by the algebraic element of the first element of the last column, and so on. And you know there is another property of the determinant. If you do it, I mean multiply elements of one column by corresponding algebraic complements of elements of another column and sum up, then you'll obtain 0. That was a property of determinant. So look, so if you multiply elements by algebraic complements of themselves, then you'll obtain the determinant, right? Why that is 0? Because look, okay, I can prove this property almost immediately. Because what it means, replace the last column by the first column, right? Replace by the first column. Then what is it? It will be the determinant of this new determinant, right? By the Laplace theorem. Because you multiply elements of the first column, which are here, right, by the same algebraic complements, right? And we know that the determinant where two columns are the same is 0, right? So that is why these are zeros. So those are zeros. In fact, for arbitrary point. But of course, you see that I should do it at a point, so I can proceed precisely at our point x0, y0, right? And if we do it at the point x0, y0, then we know even more. Then we know that is our principal minor, which is by supposition is not 0. So we supposed that delta m, which is that one, that is delta m, that is delta m, that is delta m for our point x0, y0, which is not 0. And that is precisely this term. Oh, sorry. The last is, so here we sum up elements of the last column times algebraic complements, so we'll obtain the determinant. That is our Jacobian. Then what we have? So at the point at x naught, y naught, what happens? That is not 0, and delta m is not 0 by our supposition without loss of generality, right? And what it means? Hence, psi, partial derivative of psi m with respect to ym at x naught, y naught is not 0. So our main supposition to apply theorem 1 is satisfied, right? So it means that we can apply the theorem 1. So now apply theorem 1. Theorem 1 to the function psi m x1 so on xn ym. So then what we'll obtain? For arbitrary epsilon m greater than 0, there exists delta positive such that for all x in the cube, now that is n-dimensional cube, before the cube k delta 1x not tilde was n plus 1 dimensional. Now we have n-dimensional cube, that is n-dimensional cube, such that for those values of x, we can define the function ym equals to phi m of x1 so on xn, such that for all x ym in the product k delta x naught times ym naught minus epsilon m ym naught plus epsilon m, the equation psi m of x1 so on xn ym equals to 0 and ym equals to phi m of x1 so on xn, they are equivalent. That is precisely by theorem 1. Okay. Now we have ym as a function of all axes, right? And we can define now yj equals to phi j of x1 so on xn by capital phi j of x1 so on xn and phi m of x1, so on xn. So you see, functions phi j's were defined before, right? And now we substituted ym as we solved from the equation for capital Fm, right? Then what we have? Look, now you see that for arbitrary x in k delta x naught, right, we have yj equal to phi j of x1, so on xn, j from 1 up to m. Now I collect the information together. Yeah, here I should write j from 1 up to m minus 1. So from 1 up to m minus 1 we defined now. For m it was defined just before, right? And for all points x, y in k delta x naught times product j from 1 up to m yj naught minus epsilon j yj naught plus epsilon j. The system, this system, and that, the original system, fj of x1, so on, xn, y1, so on, ym, they are equivalent. That is what I want. But of course, at the moment, I have no equivalence yet. What I know only implication, right? Why we have implication? Because if yj's are defined as follows, then we know it's like embedding of one system of equations into another, right? If we substitute, look, so we know when we substitute yj's are equal to capital phi j for arbitrary ym into our first m minus 1 equations, then we have identically 0 for arbitrary ym. So first m minus 1 equations in this system are satisfied because of that, and here it was valid for arbitrary ym. And the very last is satisfied because what is psi m? What is psi m? Psi m is precisely the last function capital Fm when we substitute phi 1, so on, phi m minus 1, right? It means if we substitute those values of yj's. But in principle, we can obtain non-uniqueness, right? So it means we need to prove that converse is also true. How to do it? By contradiction. By contradiction, suppose there is another possibility to solve that system of equations in our set. So suppose there is another system of equations let's say phi j hat, another system of functions, sorry, j from 1 up to m, which also satisfy all those suppositions, right? Then look. Then we'll proceed as follows. So fix ym hat, right? So ym hat is fixed arbitrarily. Then look at what is written here. We have m-1 functions, that is fixed, right? We have m-1 functions with hats, right? Such that if we substitute here those functions, right, with hats, then we have equality, right, for m-1 functions. And also, all of them are in this product, right? But then, as we know by construction, it means that, you see, if this is satisfied and ym hat is here, right, then all those yj's should be just capital phi j's, right? So by our construction, we have that yj's hat are precisely phi j's, capital phi j's of x1, so on, xn, ym hat. Yeah. And then and then if we substitute them into our last equality, what we'll obtain? We have this equality, right? This function, psi m, right? So when we substitute them, all of them here, j from 1 up to m-1, if we'll substitute all of them into the last function, capital Fm, then we'll obtain precisely psi m of x1, so on, xn, ym hat, right? Because here we have the same functions, but with hat here, So we'll obtain psi m with everything x's are the same, but ym is with hat. Which is 0, of course, right? For the related domain. But now, remember, we had, by theorem 1, uniqueness, right? So if psi m with ym hat equals to 0, then ym hat is precisely phi m, our function phi m, without hat, right? So then it follows that ym hat equals to ym, as we defined, right? And after that, go back to here, and we'll obtain other yj's are equal to yj's hat. So our supposition that there are other functions is not true. Okay, The last assertion about differentiability, why it is satisfied that all functions are differentiable. That is because of construction. You see, all functions capital phi j were differentiable by induction hypothesis, right? And the function psi was differentiable, hence by theorem 1, function phi m is differentiable, and then we substitute into differentiable function, hence we have again differentiable function. So the last assertion is proved as well. Okay, so theorem is proved. Yeah, theorem is proved. Now, how to compute partial derivatives? I think the best way is to look at what happens in an example. I mean, rather theoretical example, which shows how it works. So, if you remember, for theorem 1, the formula was given inside the theorem for the partial derivatives, but it was easier to deduce it just by differentiating the equations. So similarly, we can proceed here. So let me consider an example. But that is theoretical example. I mean, no explicitly written functions, just will fix m and n. So n equals to 3, m equals to 2. So it means we have two functions, f1, variables x1, x2, x3, y1, y2. This is 0. And f2, x1, x2, x3, y1, y2 is 0. We want to solve this equation. So we solve it by using theorem 2. So we can find two functions of 3 variables. Now the question how to compute partial derivatives of those 5 functions. So what we'll do? We'll substitute those two functions into our capital F1 and so on. And then we'll obtain identities. Those are identically zeros. So we have two identities with respect to variables x, and we can differentiate with respect to each of those variables. For example, let us compute derivative with respect to x1. So what is derivative with respect to x1? df1 with respect to x1, also where we can find derivative with respect to x1. df1 with respect to dy1 times partial derivative of phi1 with respect to x1 plus partial derivative of f1 with respect to y2 times partial derivative of phi1 with respect to phi2 x1, and that is 0. And also similarly partial derivative with respect to f2 we can differentiate with respect to x1 everything. What gives that one? Recall, I want to compute partial derivative of little phi's. So we look at this system as a system of linear equations with two unknowns. Partial derivative of phi1 with respect to x1 and partial derivative of phi2 with respect to x1. The matrix of this system of equations is that one. That is the matrix of our system of equations. So our system of equations in the matrix form can be written as follows. Oh, sorry. Yeah. So I wrote our system of equations in the matrix form. Now, how to compute that vector? We can use inverse matrix, right? Why we can do it? Because what is the determinant of this matrix? It's precisely our Jacobian, right? Which is not 0 by the supposition. So the matrix is invertible, hence we can find the inverse matrix, and we'll obtain the following formula for the partial derivatives with respect to x1 minus the inverse matrix to that one the inverse matrix times this vector. Right? And of course, in a similar manner, we can compute all other partial derivatives. So that is how to compute partial derivative with respect to x1, sorry, x1 here. And in a similar manner, we can find partial derivatives with respect to x2. That is minus same matrix minus 1 times similarly partial derivatives with respect to x2 I here. And similarly for the third. And then, or maybe I will not do it, because now we can understand how to unify them in a matrix form, right? So in a matrix form, we can write like that. This is 2 by 3 matrix of all unknown derivatives, right? And it can be written as follows: minus the inverse matrix to our Jacobian, the inverse matrix, and then 2 by 3 matrix, which is once again consists of all partial derivatives. Yeah. And it gives the way how to write in general. So in general, if we have, let me firstly give a definition, notation better to say. So Jacobian matrix is that one, which appeared before. It was just Jacobian. It was Jacobian of that matrix. Now we have the matrix itself. That is M by M matrix, M by times M matrix, right? Or let me, yeah, J, right? J, M, F1, so on, F, M, right? And then how to compute partial derivatives in general. So the matrix partial derivative of phi with respect to x1, so on phi 1 with respect to xn. Yeah. So on phi m with respect to x1, phi m with respect to xn. That is m times n matrix can be obtained as minus the inverse to the Jacobian matrix times the matrix of partial derivatives similar to that one. So that is also m times n matrix. Yeah. So that is how to compute partial derivatives. So similar formula to what we had before, but in theorem 1 we had matrix 1 times 1, so it was just a number. 1 by that partial derivative times derivative and times derivative. Not derivative. We had vector of partial derivatives 1 by n matrix, in other words. So that is the generalization of formulas of theorem 1. Okay, that's all for today. Thanks for your attention.